study maths at university?
Yeah, Marcus, it's a good question. Maths for me was very much an obvious choice. At the time, I thoroughly enjoyed the sciences. I liked sort of physics and all the precise answers of engineering and physics and chemistry and things like that, and particularly mathematics. And I had the sort of brain which enjoyed working the numbers and actually writing. I found writing long sentences, so English and geography and things like that, where I had to give written answers, I got quite bored doing all the writing, and I used to want to skip bits. Whereas with maths, there's much less writing. I have to say I still used to skip bits, and I still used to get told off, because with mathematics you actually have to put down a full argument of how you do each step. And I used to skip between bits because I could see where I was going with the answer. So I used to get in trouble with that. But when you got to the answer, you knew you had the right answer, and it was very satisfying to do. So that was very much, it was not only something I enjoyed, but it was also the way my brain worked and the way the sort of precision of it, because I was very much into detail when I was younger. So natural choice for me.
How has maths helped you as a pilot and a land speed record driver?
That is a very good question. Mathematics, from my point of view, is the best possible background. And probably the best way I've ever heard it explained is that mathematics is not actually a science. Mathematics is the language of all the sciences. So whether you're doing physics or engineering or whatever it is, you have to understand the maths to be able to manipulate all the concept. In the same way that when you're talking to somebody, you have to be able to speak English. So maths is very much the language, and it's not only a great language to understand the dynamics, the speed, and the turning and weapons parameters, and how much fuel you've got and how long it's going to take to get somewhere for flying a jet fighter. It's also a fantastic way to understand exactly the same sorts of problems with structural loads and the dynamic problems and the amount of thrust you need and the amount of weight for a land speed record car, when ultimately you're trying to achieve a mathematical number which is the shortest time possible across a measured mile in the middle of a desert somewhere. So it is actually, in essence, a mathematical challenge, and maths is a brilliant way of thinking about it.
What is the highest speed you've achieved in an aeroplane, and has maths helped you when you've had problems at high speed?
I think probably the highest speed, well there's different ways of measuring speed in an aeroplane. This gets a bit complicated now, I'm afraid. You can measure it compared to the speed of sound, so whether you're supersonic or not. So Mach 1 is the speed of sound, Mach 2 is twice the speed of sound. So I've actually been at twice the speed of sound, Mach 2, at very, very high level. Now that, in terms of how fast you're going over the ground, is about, it's over 1,000 miles an hour, but I was at 50,000 feet at the time. Down at low level, so close to where Bloodhound is going to be operating, because the air is much thicker, aeroplanes travel slower. So that I've managed maybe 850 miles an hour, flat out at low level, which is actually quite good. There's no jet fighter in the world that will do 1,000 miles an hour at low level. So it's quite exciting to be building a car that will go faster than any jet fighter at ground level. I've been close, but I haven't been that fast at low level, so that's going to be quite exciting. And in terms of having a problem at high speed, mathematics is a great way of thinking about the problem in terms of how fast you're going, how long you take to cure the problem. Like, for instance, if you have an electrical problem in a tornado, you have to land the airplane within about 20 minutes because you'll run out of electrical power. So knowing how fast you have to go to get to an airfield to land it safely and shut the airplane down is a very useful thing to be able to do. So again, as far as I'm concerned, maths is a brilliant background for both pilot and as a driver.
Which aeroplane have you enjoyed flying the most?
Or which aeroplane I've enjoyed flying the most? I'll give you 2 or 3 answers and then I'll try and choose from one. I was, obviously, any pilot remembers the very first aeroplane they flew and the very first aeroplane they first flew by themselves, did their first soloing. And that for me was an aircraft called the Bulldog. It's a little propeller-driven aircraft. But the first aeroplane I got in, I just went, oh, I love this aeroplane, was the first fast jet I flew, which was the Hawk trainer. It's the same aeroplane that the Red Arrows fly. and that's it's a big long bubble canopy, so you've got fantastic visibility. It's very, very sensitive control, so it's great fun, very easy to fly, and it's very fast, 500-600 miles an hour at low level, so it's fantastic fun. And I did all my advanced jet training on the Hawk. I then moved on to the Phantom, which was very much a huge war machine, 25 tons fully loaded, the most enormous 2 engines, each delivering 20,000 pounds of thrust. Absolutely incredible aeroplane. Loved flying that. And I'm lucky enough now still to be doing some flying. Now I have to pay for it myself at the weekends, but I have a share of an aircraft called the Extra 300, and that's brilliant. Ask me now which one of those aeroplanes I would like to go and fly tomorrow. The Phantom. So that's my favourite aeroplane.
You can't put Bloodhound SSC in a wind tunnel. Can you explain how computational fluid dynamics helps you design it instead? Yes.
The tools of computational fluid dynamics, without them, we could not build Bloodhound. We couldn't build a safe supersonic car. And the reason is this. You can take a supersonic wind tunnel, you can build a wind tunnel, blow air through at 800, 900, 1,000 miles an hour, and you can put a model inside the wind tunnel. But the problem is you've got to simulate the flow over the top of the car. Well, that's easy. That's the same as aeroplanes, just the air going over the top. You also need the flow underneath the car, between the car and the ground. And what you're trying to simulate is a car passing over the ground at 1,000 miles an hour. In a wind tunnel, if the car's still, you have to have the ground going past at 1,000 miles an hour. And there is no way, physically, it's not possible to build a rolling road, a conveyor belt, that will do 1,000 miles an hour. The fastest moving road wind tunnels are maybe 100 miles an hour, so nowhere near fast enough. So we can't possibly simulate, we can't possibly measure what's going to happen to Bloodhound. The only way of doing it is to do it in a computer by simulating the airflow and actually modelling it. And again, to make sure that we understand what's happening and to be able to validate the computer, because it's easy to generate rubbish with computers. It's very easy to generate the wrong figures if you don't understand what you're doing. So to have real-world experience with modelling and testing is invaluable. We did that with the thrust supersonic car in the early 1990s. We then, of course, ran thrust SSC in 1997 and went supersonic. We have all the data from that, plus all the computer modelling, so we can regenerate all of it. We now know that because we can recreate that data, the computer model works. So that's a computer model I can actually look at and say, I trust this because I know it works. Here's a real example, a car I drove. We can reproduce all of that data. We know that that's a good model because it understands exactly what's happening. Now we just change the shape of the car, different model, but it's the same computer program, modelling the airflow for Bloodhound. I can then say, I trust that, I know, if it says the car will stay on the ground, we've got the right shape. And if it says it's thin enough and we've got enough power to do 1,000 miles an hour, I know that the car is fast enough. So that's what's given us the confidence, and that's why computational fluid dynamics is absolutely essential for the land speed record today at the sort of speeds we're doing.
Can you tell me what the timetable is for Bloodhound SSC? When will it first run here and in South Africa?
I would love to be able to tell you exactly when we're going to do this. The overall picture of Bloodhound, we initially said we would do probably 2 years of research. We would then do a year of detailed design, and it would take a year to build it. That was 4 years ago, and we've only just started building it. So obviously we are a year and a half behind. Why is that? First of all, the 2 years of design took 3 years. And it's that extra year of computational fluid dynamics. It was so much harder to find the perfect shape. Well, it doesn't need to be perfect, it needs to be good enough. It needs to stay on the ground all the way through the speed range, which is incredibly hard. And it took us an extra year to find that shape. And we learned a lot, so it was very useful research, it was very important to do, but it actually took nearly 3 years to do. The detailed design then actually took almost a year to get ready to build the car, and we have now just started to manufacture the car. Now the next question, how long will it take to manufacture, and when will it be ready to run? If everything goes well, and all the contractors are able to deliver exactly what they say, and this is a prototype, no one's ever built one of these, so it's just their best guess on how long the metal parts will take at the back end of the car, how long it will take to make the carbon fibre. make sure that they exactly join in the middle, because there's a bulkhead behind the cockpit. I'm sitting in a carbon fibre tub, and just behind me is the metal fuselage at the back end. They have to join perfectly and be bolted together. So if all of that works perfectly, we will be ready. It's now early 2011. We should be ready to start testing the car about the middle of 2012. And then, of course, also we need to earn some more money to pay the engineers to do that. So there's a bit more sponsorship to come in. And as all the engineering companies working on it need to deliver it at the right time. So we may be a bit late. Somewhere middle of 2012, we should be testing the car in the UK. And we'll initially test on a runway. That testing will then take 2, 3, 4 weeks of checking the engines, the systems, the suspension, the brakes, all of the car's dynamics and data systems to make sure we're ready to go to the desert. And if there are any problems, we're going to have to stop, we're going to have to fix some things, have another go on the runway. So this could be maybe 6 or 8 weeks at least. Then, if we've got enough time before the rainy season starts in South Africa, we can then go to South Africa in 2012. If not, 2013. So here we are, early 2011. Let's call it about 2 years plus or minus a bit.
Thanks, sir, and good luck with the land speed.
Brilliant. Marcus, thank you very much indeed. Thank you for a great set of questions.